Hello and welcome to this short presentation and demonstration about the eVM virtualization platform for Windows. The eVM virtualization platform, in conjunction with multi-core processors, gives you a means by which you can combine multiple independent systems into a single solution. With eVM, it's possible to support Windows alongside your RTOS or embedded OS on a single multi-core processor, with your embedded OS running on a dedicated core at full speed. The benefits associated with such a system are lower cost, smaller size and footprint, increased performance, and the ability to move your system forward onto modern and less expensive hardware. Why would somebody choose an embedded VMM over the more traditional solutions that are being offered for servers, such as those from VMware, Microsoft, and Citrix? Well, the big difference has to do with determinism and access to I/O. In those server solutions, your I/O is all virtualized and is optimized for network-based server applications. If you've got a specialized I/O card, such as a field bus card, an A to D card, a counter timer card, whatever it is, you're not going to find it in the virtual machine inside a VMware system, for example. You're only going to find those devices that the virtual machine presents to you. Anything outside of that is lost or forgotten. Likewise, determinism on the Tenasis eVM solution is dealt with by ensuring that your virtual machine, which is running your legacy OS, your RTOS, always has a dedicated core in a multi-core CPU, as well as dedicated RAM, the virtual devices, and real I/O devices that go along with it. So if an event occurs that requires microsecond response, you'll get that inside the Tenasis eVM virtualization machine. You won't get that inside of a server solution. That virtual machine might be set as idle because a different machine is being serviced, and so it may be milliseconds or even seconds before you're going to get a response. You've always got a dedicated core in the Tenasis eVM solution to ensure that your application can respond to external events at the moment that those external events occur. Now, in the demonstration that follows, we are going to be showing Tenasis eVM running on a quad-core system. In that case, Windows will be running on 3 cores, and Windows CE will be running on a single core. In that system, there will be a virtual I/O device, an NE2000 Ethernet adapter, which will connect to the Windows system through a virtual cable and an NDIS driver on the other side. Likewise, there will be some virtual COM ports, which will have a virtual serial cable connected back to Windows, which can then monitor output and input on those serial ports through a standard terminal emulator. In addition to running Windows CE, we will run and boot QNX and VxWorks. Okay, let's start the eVM system first with Windows CE. I've selected my Windows CE image. I've got 3 images here, QNX, VxWorks, and Windows CE. I'm going to start that image, and what we will see here is I've got a terminal emulator attached to the COM port of that image, and it's asking for us to boot. And we are going to connect through the virtual Ethernet to that system and start downloading our test application over that virtual Ethernet connection. So Visual Studio is running on Windows, and Windows CE is running on its own dedicated core. And here's our test application. It's a very simple application. It has a breakpoint in it. It's going to execute this infinite while loop when it starts running. Now, since we're in debug mode on this, it'll take this a little bit after it has finished downloading to actually start operating where we can use it. You see there's a whole bunch of things going on in here, and there's more work taking place in the Visual Studio development environment. So while we are waiting for this to get to the point where, to get to our breakpoint, we can take a look at some of the features here in the eVM control panel or configuration panel. But we have 2 COM ports configured here. These are virtual COM devices. they appear as real hardware to the Windows CE image, and so Windows CE is using its real COM device driver to speak to this, but it's being provided as a virtual device by eVM and connected back to the Windows side through a virtual COM port over there. And so this Windows CE image has been configured so that COM1 is where it will provide all of its debug output and so forth. And that's what we're seeing on this terminal emulator on the Windows side. Likewise, we've got a standard PIT and PIC on here. We've got the ability to see devices on the PCI bus, and we've also got a virtual Ethernet adapter in the form of an NE2000. Like the COM adapters, this is also a virtual device, and it is in fact what's being used for the connection, the network connection between Visual Studio and the target Windows CE. Now we have gotten to our breakpoint within this application. You can see, as you would in any Visual Studio debugging session, we can watch local variables, registers, and so forth. We're going to just step through this application, and if you watch down in the local variables here, you will see these numbers change as we step through the application. You'll also see the register change with each iteration of the application. Okay, so let's stop debugging and disconnect. And we're going to end this session. And now I'm going to start the VxWorks session. And again, it has been configured to send its output to the COM1. So it sees a COM1, which appears to be real hardware. It sends that through a virtual connection to the Windows side, and from there we can speak with or communicate with this VxWorks over its serial port. That's about the extent of my knowledge with VxWorks. Again, because there is an Ethernet connection available, we could have the VxWorks Tornado development environment running on the Windows side, connected to this VxWorks virtual environment on the dedicated core, and we would be able to use it as though it was a separate machine. Now let's do the same with QNX. We'll start the QNX image, and as it boots, we will see the output show up here on our terminal emulator, which is connected to the COM1 port on the QNX kernel. You can see we have the QNX kernel image running in the eVM virtual machine. We're connected, in this case, over a virtual or serial port connection. Likewise, since QNX has access to this NE2000 device, this virtual Ethernet connection, we could have the Momentix development environment running on Windows, connected over the virtual Ethernet connection to the QNX kernel running in the eVM virtual machine, as though we had two separate machines, but all on one. Let me show you a little bit about this particular system. This is a quad-core machine, as I mentioned earlier. It has a virtual Ethernet adapter on the Windows side, which connects through to the NE2000 device on the eVM virtual machine. There are two COM ports here. Each one is connected to the virtual COM ports on the eVM machine, as there's a serial cable, basically a virtual serial cable between this COM3 and COM1 on the virtual machine. That's why you saw COM3 in the terminal emulator window. And then here are the four cores that are part of this processor. If we look at Task Manager, we see only 3 cores actually being owned and run by Windows. That is, Windows is running in SMP mode, but on 3 of the 4 cores, because the 4th core is being used by eVM to support the virtual machines that QNX, VxWorks, and Windows CE were running in this particular demonstration. In an eVM system, there are 2 classes of I/O devices, virtual and real. Real I/O devices are those in which there is no virtualization. The connection between your application, your operating system, device drivers in that operating system are direct to the hardware. It's no different than running on standalone dedicated hardware. When you've got a real device plugged into the system that's been partitioned for use by your legacy OS on the eVM system, it's talking directly to that hardware. Virtual devices, on the other hand, are talking to a piece of software that is simulating real hardware through the eVM platform. That is, the eVM Virtualization Manager is providing these virtual devices so that your software can interact with what it believes to be real hardware. Some of those are examples that you saw in the demonstration were the interrupt controller and the timer, the pick and the pit. There is an IDE interface, and you saw 2 COM ports and an Ethernet, an NE2000 Ethernet controller. All of those devices are designed so that standard existing device drivers can be used with them because they appear and respond just like their real hardware counterparts. Other reasons for virtual devices to exist in the eVM system would be to simulate old hardware that's been removed, but you still need to continue to use software to talk to it. For example, old VME bus interface or multibus interface, or to remap hardware to a preferred location. For example, you might partition a COM4 device to be used as a COM1 device in the virtual machine, and so you simply need to remap the I/O addresses so that your software, which wants to talk to a COM1 device, in fact talks to the COM4 device. The other thing you could do is you might have a real A/D controller that you are talking to simulate an old one, and so you have to respond to the register set of the old one, translate that into the new device, and then respond with the data back in the format that the old one would provide it. Simply as a way, for example, to bring legacy software forward on the virtual platform. So these are some of the reasons that you might use a virtual device in this environment. Thank you for taking the time to view this video. I hope it answered some of your questions about the Tenasis Embedded Virtualization Manager for Windows.